some loss function which you want to minimize. And more generally, you could have any function with no loss. And so f could be some loss function, or it could also be some loss function plus some penalty for regularization. Like if you remember last classes, we had penalty lambda. Right. So that could be any of these things. And yeah, okay. And now your essentially your goal is to minimize your function. So you want to find the vector w, your hypothesis w, which minimizes your function. And we saw from previous classes that indeed, if you can do this for a reasonable f, so for instance, if you can do it for an f like this, where this problem of minimization, this loss or this thing, has a property that your losses are convex and Lipschitz, which means that your gradient is not very large or smooth over bounded parameters. So we had some loss like this, and your parameters that you completely against are bounded, then indeed you will be able to learn. Right? So we showed this analysis using stability. And we got these, So that was the picture. So indeed, to be able to complete the story, you have to also have an algorithm which tells you minimization for you. You should be able to minimize this thing right here. So it did not even algorithm, I just said that if you can minimize this, then you're done. And goal of today is to give an algorithm which minimizes this. Okay, so so some function f which may be used like this. And we can assume that f is perhaps convex because here this setup you have to talk about convex losses. So f is perhaps convex and perhaps it is Lipschitz or it is smooth. Plus, if your lambda here is large, this function here for a convex loss is 2 lambda strongly convex. So we can also assume that this function here is also strongly convex. So now we can kind of forget what this exact expression was. We can forget what exact f looked like, and we just talk about an arbitrary f, which has these nice properties. And we want to minimize this. Okay. So that's the setup. I'll erase this now because we don't need it anymore. Now, okay, so here's a very simple algorithm for this, which is called gradient descent. And the algorithm can be stated in this one line. So you start with an initial W. So let's call this W0. This is some initial W. Maybe it is all because perhaps. And then you update this W in a sequence of steps. And the update step, so W at step t plus 1 is W at step t minus, yeah, so you change this WT. How do you change it? So you move in the direction of the negative gradient of f at W. So you find the gradient of f at W. It is negative, and okay, so that's the direction in which you move. And maybe you want to multiply this by some eta is a positive thing. So this controls how much you move. So more eta means that you move. So that's the gradient analysis. And pictorially, it just means that. So we have, so it's also called hill climbing or hill descending, because if you think of let's say you have 2 dimensions, then I can think of my function as a hill. So function is a hill, could be some terrain. So think of W as being maybe surface of the earth, just flat surface, but just flat for now. So you have this, so W is your surface, and your function is essentially the terrain. So the higher the so terrain height is like the function. So height at a point is like the function, and you're essentially trying to find the lowest point in the terrain. Minimize the function means that you find the point with the lowest height. And then what is gradient descent saying? It's saying that if you are at some point, if you're standing at some point, you just look locally, look around you, and look at the direction where the function is decreasing the fastest. So where the ground is sloping down the fastest. So maybe if you look here, ground slope like this. Go to the right, ground slope like this. So so this says that hey, move to this direction. So if I'm here, so this is WT. The WT plus 1 should be on this side. Because that's kind of the story. It's also about steepest descent. To move in the direction of where you are decreasing fastest. So that's how you visualize it. So you want to find the point with the lowest height in the terrain. You look where you are, and you see that okay, around me, which direction should I go so that the ground is sloping down the fastest. The most steep slope. That steep slope is just this direction. Negative gradient. Okay. Okay. So this is a very famous algorithm. It's very easy to state, easy to visualize also. So it's very widely used in practice. Okay. So let's talk about this algorithm today. So we'll try to analyze this, and we'll show that for Lipschitz and convex functions, this algorithm is good. This will indeed find. This will indeed find at least an approximate. Also, a couple of more comments. So, when I talk about convex and Lipschitz function, so this may not be differentiable necessarily. So for convexity, you don't need differentiability. However, when I talk about a gradient is derivative. So this implicitly assumes that the function is differentiable. So the function is not differentiable, but it is convex. Then you can replace it by something called a subgradient. So then you replace gradient by what's called a subgradient. Okay, so I'll talk more about this in detail later. But the point is that this can actually be handled. And let me just give you an example of subgradient. So subgradient is just something which can play the role of a gradient in the definition of your convex function. So yes, so if you recall how we can state complexity in terms of gradients. So we said that okay, so here is the one notion of complexity. Let us write it here. So so F is convex. Okay, so a differentiable F is convex. If I don't leave. So I will give you a different definition in terms of gradients, maybe. So here is my so for every x f of y is at least from x y is at least x plus gradient of f. So this is an alternate definition of complexity for differentiable functions. And why does this look right? Because if you remember the Taylor series, the Taylor series will say that f of y is equal f of x plus some first order term plus some second order term, which is like derivative, right? Minus x squared. And for convex function, this is positive. Therefore, this will always be okay. So then this one of y is right. Okay, so that's for differentiable f. But if f is not differentiable, okay, what about not differentiable? So arbitrary f is convex if for every x and y there is some vector. There is some there exists some vector v so that this is true. So and indeed for differentiable f you can take v to be the gradient, and for non-differentiable f there will always be some vector like this which satisfies this constraint, and a vector like this is called a subgradient. Any v like this, any v that satisfies this equation for x. So for a given x, any v which satisfies this is called okay. When this satisfies, it should satisfy for given x for all y. It's called a subgradient of x. So give me an x and give me any vector v which satisfies this for every y. Okay, so a single v which satisfies this for every y. Or maybe it's better to write as for all x. Okay, yeah. Okay, probably I think I wrote it probably. So for all x, then like this for v. So that this is true for all y. Good. Yeah, so any v like this for a given x is called a subgradient. And so let me give you an example of such a v for non-differentiable f. So let's take f to be absolute value of x. So let's say x is one dimension. So your function graph looks like this. Okay. So that's its function. So indeed, at x equal to 0, this function is not differentiable. So can you tell me a subgradient at x equal to 0?
Y equal to 0.
No. So remember that. So what are the dimensions of the subgradient? V has the same dimension as x, because I need to inner product this with y minus x. So the subgradient must also lie in R. So yeah, and by the way, there's also a notation for this is called limit. People denote it by the partial sign. So set of subgradients is denoted by this. So that's the partial f at x is typical notation for set of subgradients at x. So sorry, 0. Yeah, indeed, right? Because very good. Because indeed, for every y, f of y is at least 0, right? So indeed, 0 belongs to this. Yeah, good. Now, can you tell me the entire set? So, can you tell me all of the subgradient at 0? Yeah. So, what are all the subgradients at 0?
It would be infinite.
Yeah, that would be infinite. But can you characterize that set? So, remember, I want that the entire function should lie above this linear approximation, right? So, for a given v, this thing here is a linear function of y, right? So here, so here, what is this function? So RHS for this particular function is f of x, which is 0, plus v times y minus 2. So this is just v times. So for what values of v is f of y at least v times y? Yeah, exactly. So this is true whenever v is in minus 1 plus 1. Therefore, this set is exactly minus 1. Okay, yeah. So that's what subgradient is. And indeed, one can show that a function is convex if and only if subgradient always exists. So subgradient exists for every x, then only then it is convex. So indeed, for a non-differentiable convex function, one can place any subgradient of f at a group. Great. Also about Lefschetz functions. So if f is Lefschetz, then okay, so then as you might expect, the subgradients will always be bounded. So low Lefschetz, then for all the okay, yeah. Anyway, so that's kind of the story. Okay, but I will leave it at this in more detail later. But it's just to tell you that all of this can be done even for non-differential functions. Okay, great. Now let's get back to this algorithm. And for now, let's talk about differentiable functions. It's easy to talk about, and then I'll say some words about non-differentiable functions. Okay, cool. So let's start with proving a theorem about this. So let me state it here. Okay. So here's the main theorem. So f is convex and Lefschetz. And now let's say if I run gradient descent for capital T steps, starting at 0. Yeah, so I want to analyze how far my W capital T will be from the optimum for W star for F after T steps. So let me just say a few words also about the parameters. So let's assume that so W star is the minimum that we are competing against. W star is the minimizer of F. And recall that we only compete against W's with bounded norm. Otherwise, learnability is really not possible. So we assume this here. So if I set eta carefully, so if I choose eta to be d over rho root d, so if I choose eta like this, then you can show that then f of wt minus w star. So this is the ideal w. This is as well as you can do with bounded norm, and this is our function value. This is at most 0. So that's so what it tells me is that I can make this difference as small as I like, because this decreases as 1 over root t, b and rho constants. So yeah, so if I want this to be like epsilon, then you choose t to be d square rho square over epsilon square. Okay, so that's theorem which I want to show. Erase this one now as well. Put the other one. Okay, great. Okay, so to prove this, we proceed in 2 steps. So okay, so okay, so to make the life easy, we will not show exactly this, but we will show something slightly weaker. So instead of talking about WT, I will talk about an average W. So let's define W hat as 1 over T so this is the average W over T first T iterations. So I will show this for the average W. This is good enough because I can just average out over whatever W's I have seen. So Yeah, so I will show this instead. Okay, so let's begin by writing out some equations. So f of w hat and now note that this is actually at most. Oh, sorry, this is the other. The T goes inside. So I just replaced W hat definition. And now, and now since f is convex, the function at some linear combination of points is upper bounded by the same linear combination of the function values. And yeah, so the way to remember this is just this section. So here is convex function. Give me 2 points, W1 and W2. This thing here is f at the middle. So this thing here, this thing here is this point, and this thing here is the average of the f values, which is the point on this line. This is the line connecting the f values. The average is just this point. So indeed, the function is at most. This one too, and but yeah, this can work for any number. Yeah, okay, so yeah, so never memorize this. You just remember this picture and just. Okay, so by the way, this is also called Jensen inequality. This inequality, right? So yeah, in books you might just see Jensen inequality. Okay. Okay, so this is indeed at most this. Right. I can also take this out here. It doesn't matter. Multiply divided by t. Yeah, and at this point, I now want to use that f is convex. So okay, so till now I've just used Jensen here and multiplied divided by t here. And yeah, now I want to use convexity of f. So convexity tells me, this thing right here. So it tells me that f of wt minus f of w star. So I could take f of x on the left side, or maybe take on the other way down. Right? So I'm going to go up or down. So this thing here is at most. So yeah, so f of x minus f of y is at most the inner product x minus y. Right? So yeah, gradient of f. Yeah, so okay, so in that definition, you just plug this as x and this as y. Right there. So f of x minus f of y is at most the gradient of subgradient at x in a product x minus y. This w minus. And yeah, so yeah, right, I written the gradient of multiplicity. but you could also just put any subgradient and great. So this means that our task is really to to upper bound this point. And also since this is a linear function of WT, since W star and okay, sorry, should probably write. Sorry, I'll write W. Let me write X properly. X is WT. So this here is some linear function of W star. And so I could take W star outside as well if I like. But okay, for now I'll just stick with this. Okay, so yeah, goal is to invest about this quantity. And yeah, let's proceed to do that. So we will now show the following lemma. So that's the key to everything. So maybe I'll write the lemma. Yeah, okay, so this I don't need to write anymore. This you can. Yeah, so this I'll just draw. You know this now. So give me any function f, and yeah, give me any update of the type wt plus 1 wt minus eta vt. So vt is now any vector. So vt is potentially this gradient or it is some subgradient. Like, I don't care exactly what it is. So what you can show is that if you have any bit of this type, then this sum here with this as vt. So wt is at most this is going to be at most w star square over 2 eta plus eta over 2 that will be so that's the key now. So let's just stare at this. So since it give me any v, I don't care what it is. If you have an update of this type and you have this w0, yeah, then this sum of these inner products will be bounded by this quantity. So you take a w star, you square it up, divide by twice this eta, and then you add eta over 2 times the squared sums of the squared norms of these VTs. Whatever VT you update, that's the upper bound of this. Okay, so why is this useful? So recall that, so if your function f is convex, then you can do all the manipulations, and you can get this as your upper bound on this. And further, if f is also Lipschitz, row Lipschitz, the gradient has bounded norm, which means that all these VTs have norm at most row if it is row Lipschitz. And even if f is not differentiable, I could just take VT2 subgradients and their norms are also at most row. So yeah, so indeed, both cases I have a row here, and therefore using this I can get this at most 1 over t. Now, okay, so non-W square is at most p square because I'm minimizing over bounded non-W's. So I can put p square here, and I can get 2 eta plus eta over 2 times T rho square. Yeah. And then if you can just check that if I put eta to be this thing here, then I will get this thing to be equals this thing. Just plug and check. Great. So so all I have to do now is show this. Yeah, this is the key to prove it. Together with this complexity analysis. Great. So let's do this. As it is. So proof. So this first idea is to just understand this term. So we have this term here. So I want to somehow express this in terms of squares. So I will use some kind of square formula of so there is square formula that WT minus W star minus VT square. So I'll square this up and I'll think of this as the first vector, this is the second vector, and try to get some interval like this. So this is just twice. That is always true. Now I replace this property. So by the way, I want to also update one more thing here. So so recall that this quantity right here, WT. Instead of VT, I want to put eta VT because I have an eta update here. So I can also get. So I will also get term like this. I will put an eta here. So I will put an eta here, and then I will get an eta square here. Eta square. And I will get an eta. And now the nice thing is that this is very much in that form. So WT minus eta VT is just WT plus 1. Okay. So I can replace this by WT plus 1 minus W2. So this allows me to express the thing I wanted in terms of the things in terms of some other things which I know. Maybe I want to express it in terms of the update WT plus 1, the current WT, and this update, this vector VT. So this is just 1/2 eta times WT minus W star square plus eta square, actually right later, nicely minus WT plus 1 minus W star square. Plus eta over 2 good. And now let me just add this up from 1 to 3. So this is an exact equality. There is no inequality right now. If I add this up, then these things will cancel, as you can probably see. So I will get a summation of this. T will be 1 by 2 eta. So I'll get just the last term, which is minus W capital T. Actually, add from T minus 1 because I want to get W T here. Should I get just 2? Okay, forget 2T plus 1. I want this is 2T. So I get W T plus 1 here. Square, right? And I get a, remember, here I get a W0. W0 is 0. So it's just W star. And this also sums up. And now from this you get this. So this is a positive quantity. So we throw it out. So that's it. So what did we do here? Let's just step back. Remember that we had some function f, and I was trying to look at the difference between f at this average point w hat. Remember w hat is the averaged point so far. So to find f at the averaged point, I first use the Jensen inequality or convexity to upper bound this by the average of the f's. This is f at the average, this average of the f's. And so average of the difference between f at a certain point and f at the optimum point. And now I use convexity to say that this difference is not too large. This is at most the gradient at this point times this the vector from W T to. Oh yeah, W started from W T. And finally we said, okay, give me any vectors like this, gradient or subgradient, more generally. Let's call them VD. And I care about the sum of these inner products. And okay, how do I count some of inner products? Well, just look at one inner product and try to express it in terms of things which I can capture more easily. So, I get it in terms of squares. So, how to get in terms of squares? I just ask myself that, okay, where does this inner product come? It comes if I subtract out WT minus W star and VD. Remember, we had this WT minus W star minus VD. If I square this up, then I will get this inner product. And I want to get something of this type. So WT plus 1 looks like this. So I want to make this match WT plus 1. So I put a theta here. So that this now matches WT plus 1. And I still get it up like this when I square this up. And this allows me to then extract this out by rearranging things. And gives me this equation of squares. So tell me that, okay, this difference, this inner product is just how far you are from the optimum vector currently minus how far you are in the next step. The WT minus W star, the distance currently, distance at the next step. So this is capturing how much you have moved, how much close you have moved, right? And this is some term which depends on this update. Then I just add this up, and all these movements now cancel, and I get only the final movement from W0, which is 0, to WT plus 1 after the kth step. And and I don't really care about that because this is a positive quantity. I can remove it. So yeah, that's what this is what I find it is this.
But for non-convex things, it wouldn't work. Really.
It often does work, but not by this analysis. Because here we crucially use convexity in this term. When we replace the average by the effort average by average of moves. Although you can use a different analysis and still argue that it converges by using slightly different algorithm also. So gradient descent as such may not work. But yeah, and a simple example of that is just so any function which has local neighbor, right? So you have this, and gradient descent from here, and you get stuck here. So that's the optimum W star would. So this would be very, very fun. But under some conditions, a slightly modified algorithm can help you get there. So for instance, there are these modifications called perturbed gradient descent. So there at every moment you also add some random noise or perturbation to your WT. So you add some noise in. The noise then can help you escape these points. Because you make some random movement, maybe the random movement will help you go here. Yeah, it might help you escape this depression. If a function is well behaved. Okay, so that's still not perfect. I mean, it will not work for every non-normalized function, but for some non-normalized functions, this can work. Yeah, so we don't really have a general algorithm. Yeah, we don't have a general result like this. Okay, great. Okay, cool. So hopefully this is satisfying. It proves this here, and also works for non-differentiable functions. Okay, so now I want to talk a little bit about a slightly different algorithm, which is called stochastic gradient descent. So let's recall the gradient descent update. So let's say the gradient descent update. So you have a certain point WT, and then you just move in the direction of negative gradient. So you just put minus eta gradient of f at WT. In stochastic gradient descent, you choose this update vector in such a way that its expectation is this gradient. But the vector itself is sampled from some distribution. So you have you choose, so you do is this thing. Okay, let me keep it. Let's write it.
The distribution could be anything.
Yeah, it could be whatever. So you do minus eta Vt such that expectation of Vt is gradient of f. So Vt is sampled from some distribution. So Vt distribution D. And and indeed, yeah. So this is called for differential functions. For non-differential functions, you could write this is a gradient. Okay. Okay. So, it'll turn out that often in practice, this is a simpler task in finding the exact gradient. So let me just give you an example where this may be easier than this. So, if you recall our setup where when f was a loss function, so f was some kind of empirical loss. Loss of w on the ith example, right? Plus minus lambda. We had some f like this. So now, if I want to find the exact gradient of f at w, then I need to sum over m terms, right? Because each of these m terms has to be differentiated with respect to w. And so it needs some over m terms, which will take a lot of time. So if m is very large, then that takes the computation will be very expensive. But if I just want a distribution over vectors whose expectation is a gradient, then all I have to do is sample a bunch of these points. So maybe I sample some k points. Some k points in my fluid, and then you simply find the gradients at those k points, and you average them out.
But the endpoints must also be chosen some particular distribution.
No. So remember that in our current setup, we have some m points which are already sampled from some distribution. So that's already fixed.
But we are again choosing some endpoints of some k
points. Yeah.
The k points can they be chosen in any distribution?
Okay. So when you sample k points, you choose sample k points uniformly. So each of these k points has the same likelihood of being chosen out of these endpoints. And then since this is your objective is just an average over endpoints. If I choose k points uniformly at random and take only their average, then the expectation of that quantity will still be this. So that gives me a fast way to compute to do a sampling like this, whose expectation is a gradient. Indeed. So that's why this is a useful thing to do. Great, and that's why this is called stochastic gradient descent. Yes, stochastic because there is a random sampling here. And this is what people do in practice because in practice you have a lot of training examples here. And if you try to compute this for every example and average it out, it will take too much time. It's not feasible. So people choose some k and this sample. Okay, great. So that was stochastic gradient descent. By the way, I should call this dt here. Because for every step t, there will be a different distribution. Right? Because dt here, the distribution will depend on w. Because so you have so remember I'm sampling. So how am I sampling dt? Right? I'm computing the gradient at wt for the sample degree points. So since the point where I'm computing the gradient depends on wt, distribution also depends on wt. Or you could also have some distribution which is time dependent, and then you could say pt given. then you have to put a p here. So then they say, okay, sample PD from a conditional distribution, which is like this. Okay, anyway, there's some notation. Okay, okay, so now let's ask ourselves that how does the analysis change if I just have this register. So here, indeed, I would also analyze this expectation, right? Because there's randomness here, so I should also have expectation here. It's really, and let's have an expectation here. Okay, so if I put an expectation here, everywhere, let's see what happens. So again, expectation here. And now since expectation is linear, okay, so first so expectation, okay, so expectation first goes out, then it goes inside here. This expectation is linear, it goes inside the sum. So second expectation right here. And I can write it. And yeah, and now since again this is always true. So yeah, so I put expectation here. Great. The only difference is that instead of okay, so here indeed we have okay, so this is true for every BD, right? So this inequality is true. Okay. Oh, okay, so see, this inequality is always true, right? Yeah. So here, when I say okay, maybe I just go here. That'll be easy. So what do I have to show, right? I have to show now that expectation of this quantity is Moses. Now PT squared now is expectation of PT squared. Yeah. So notice that in all this analysis, I did not really use anything about what PT looks like. The only thing which we use is that yeah, is this square thing. Now should we get okay? Yeah. So what's the best way to say this? So, so if you look at this lemma, this is in fact always true, as you can check, because if it did not even use convexity anywhere. This is just a lemma about updates. So, the only place where we need to be careful is how we apply this lemma here. So, the difficulty is that while this is true, there is no mistake here. I cannot just plug VD here directly. Why can I not do that? Because I cannot. Okay, so the trouble is that both WT and gradient of f at WT are not random variables. So I cannot just take expectation both here and here. That cannot be so. So if I would take the expectation here and then maybe I could still try to use it directly. But but since I can't do that, I have to be much more careful. So okay, so this lemma proof works completely, right? Because if we did not use any property of the property, VD could be a random thing, whatever. This is always true. So okay, so let's now understand this step, how we connect this lemma to here. So I'll erase this proof now and let's focus on that. This is this is done quite carefully because you can't just take predictions side by side. And then there's this also. So all this works as it is. Okay, so we will show the following claim, which kind of connects these two. So the claim is expectation over. Okay, so remember expectation is over the choice of the V's. Right? We sample these V's here at every iteration. So expectation is over the choice of these V's. Expectation over V 1 through T. That's the nice notation. So sample these T V's here. And so we have 1 over T. So this is basically right. It is operated here. And I want to show that this is at most. But so this is what I have to show. Remember, this is what we had last time. So without the expectation, we had this. This was true because f was convex and VD was subgradient. Now f is still convex, but VD may no longer be a subgradient. Right? The only thing we know is that the expectation of VD is in the subgradient set. So while this inequality is still true, for some subgradient of f, this subgradient might not be VD itself. So that's why this gets complicated. So okay, so I just erase this so to confuse you. Okay, yeah. So yeah, so if I can show this, then I'm done because then this is essentially what we need. After this, I can just plug this thing right here. Okay, this is same expectation. And yeah, like I said, this lemma we never use anything about complexity or how VT is coming. This is always true. And yeah, so all this will just follow through. Okay, so let's now focus on proving this. Okay, so first let's just do some simple manipulations here. I'll just take 1 over t out so it looks a bit cleaner. And take expectation inside. That you can always do by linearity of expectations. This is so I just did some simple switching around. Okay, so now let's think carefully about this thing on the right. So let's write this as so write this down in 2 steps. Remember, I'm taking expectation here over the choice of v from 1 through t. I've sampled these t v's, capital T v's from these different distribution visual condition on these WVs. So now I'll write this in 2 steps. So I'll first go from 1 through t minus 1 and then look at last thing. So I'll write this as so I just that thing here is expectation v 1 through I'll also take this. Okay, great. Okay, great. So if I just look at this term here, so I split this into these capital T terms. Each term is an expectation, of some VT, right? And this VT now depends on the randomness in the previous, in all the previous steps. So I've written here V expectation over V1 through T, but really this only has to be. Okay, so decide now. This is just expectation will be 1 through T minus 1. Confusion or V. Does this make sense? So all I've done is I've said that okay, the choices of V after step t, after step small t, do not affect this quantity because V at step small t is determined only by the randomness up to step small t. So it's enough to take expectation only over V's from 1 through the step small t. That makes sense. And now let's look at where WT came from. So, yes. So remember the WT depends on V's from 1 through t minus 1. So okay, so let me now blow this up. That's the key. So expectation to be 1 through t. VT WT minus W1. This is now yeah. Expectation to be 1 through t minus 1. Expectation over yeah, okay, that's it. 1 through t. Given okay, so that's the if I take this right VT. Does this make sense? So okay, so what have I done here, right? So here I'm taking expectation over some t random variables v1 through vt over their choice. So I break that into two parts. I first so I say that okay, give me any choice of the first t minus 1 vectors. Now for these fixed t minus 1 vectors, so given these t minus 1 vectors, I can now take expectation. I now take expectation over the remaining vector v. So yeah, so this is a valid way to compute expectation. Instead of taking average over all my t variables, I will fix the choice of 3 minus 1 variables and take expectation over the take average out over the remaining. Then I average out this average over the 3 minus 1 variables. So this is obvious. Now why is this useful? Because inside this, I can now take expectation inside. Why? I can now say that this is minus 1 expectation given. So I've taken this conditional expectation inside here. Why can I do that? Sorry.
Yeah, there is this is the product. The other things are
Yeah. So the point is that WT here is not random if V1 to T minus 1 are fixed. Earlier, I could not have done that. So, so when I had this thing here, at this point, I could not have taken this expectation here because WT also depends on VT. Yeah, so WT. Okay, so point is WT is also random variable here. So since both of these things are random, I cannot just take expectation inside here and leave this fixed. But here, since I first fixed V1 through T minus 1, this quantity is no longer random. It's just a constant multiplier. And so I can take expectations. Great. And yeah, okay. And now, yeah, let's put brackets. And yeah, I think now we are basically there, right? So, so what does my my algorithm tell me? My algorithm tells me that after I have chosen my V1 to T minus 1 and figured out my so V1 to T minus 1, determine WT minus determine WT, right? Yeah, and then using WT, I then sample VT. Right? That's what the algorithm was. The VT was, so yes, the expectation of VT given my WT was in this variance set or no variant. So this tells me that given these equal to T minus 1, this expectation must lie in the subgradient set. Because this is exactly what my algorithm does. It has already seen 1 to T minus 1. So those are given to the algorithm at that T. And now it is sampling VT in such a way that this expectation is subgradient. And now since the function is convex, this tells me that the inner product of this expectation, which is now in the subgradient set, with WT minus W star, this is now an upper bound on this function change. And as this quantity here is so this is at most f of WT to change. Yeah. So yeah, so I haven't done anything. I just said okay, this thing here in the subvariant set, and so this inner product must be at most this. And now I'm done. So yeah, so indeed. Yeah, I mean, there's nothing more to say. So, so the point is that yeah, so this expectation here depends only on V1 to T minus 1 because WT depends only on to T minus 1. And so yeah, I can now complete the proof. So this is so therefore by this inequality right here, this thing here is at least, I mean not at least. Okay, so this is at least this is the other one. The function is below this. So this is, and that's what this is at most 1 over T. Okay, so this expectation is at most I think about. This thing. VT. So yeah, this is just the same. Yeah, and this I can. Yeah, this I now talk about that level. So let's just maybe take a step back and just see what happened. So okay, so let's just recall. Algorithmically, all we are saying is that the update vector at VT has to be in such a way that its expectation given my history so far, given my WT is from the subgradient set at the VT vector itself need not be a subgradient. Can be whatever. Only the expectation has to be. So how do we analyze this? Well, we just use linearity of expectation on this difference. So f of w hat I now upper bound by upper w hat is just f of this average because w hat is just the average. F is convex, so f of an average is at most average of f's. Expectation is linear, so it goes inside this sum here. So and we got this expectation of f of wt minus f of w star. And what I knew was this fact, right? And yeah, in particular, I would have taken this expectation here, this summation here, and this expectation could have been over V1 through T. Because here, this is better than V1 through T. Okay, and now the trouble was that I could not take expectation inside this. Yeah, I could not take inside here blindly because WT is also random variable. So the thing is to first de-randomize WT. I want to fix this. How will I fix WT? I know that WT depends only on V1 through T minus 1. So I'll say, okay, let me break it into two parts. I break it into V1 through T minus 1 so that WT becomes deterministic and then take average over the last variable. Now, since this is deterministic, I can now take expressions. And yeah, and now indeed this is a gradient and everything works out. So that was it. So no, yeah, nothing special. You just have to think carefully about what's going on, and you have to do this. You have to just think about what WT depends on and what VD depends on, and you have to decouple them by taking this conditional expectation over fixed steps, fixed V's from other things. Yeah, that's the only addition here. Okay, great. So that should be good. Next time we will continue this for more complicated things. So this was for Lifshitz. Next time we see this for smooth functions. And also extend this. It's about directions. Thursday, right? So same time.